Hello, class. So now we are in chapter 18, going through arteries and veins. Arteries and veins. So the heart pumps blood through the body, but how does it get through the body? It doesn't just pump blood and squirt it everywhere. The blood has to travel through this network of arteries and veins so that it goes to where it's supposed to go. And not everywhere in your body is getting the same amount of blood at every time. Your body can regulate that, control that. We're going to talk about blood pressure. We're talking about blood flow. We're talking about capillaries, arteries, veins, venules, and how blood moves through the body. Let's go. All right. So the main transport mechanism is the blood vessels. Transports blood to the tissues, and that's where gases, oxygen, carbon dioxide can transfer in and out of the blood. Nutrients, things that we eat, go to the bloodstream, transfer to the tissues. Waste is exchanged. Remember, cells produce waste that has to be removed uh, and transported. Blood vessels help to regulate blood flow. They can control blood pressure. Remember, or maybe not remember, but we will learn about how blood vessels can constrict, vasoconstrict, vasodilate. Something's constricted, obviously the pressure goes up. Dilate, the pressure goes down. They also secrete some chemicals, which we're going to talk about. And there are two circuits. So there's the pulmonary. Think of pulmonary, think of the lungs, and then there's the systemic, which is the heart. So pulmonary transports blood between the heart and the lungs. The systemic circuit transports blood between the heart and the rest of the body. So two different circuits, which are very important, clearly, because the oxygen that we breathe in has to get into the bloodstream, pulmonary circuit, and then that oxygenated blood needs to then be transported through the body so that it can get to the body, the systemic circuit. So two different circuits, but they're working together to get oxygen to our entire body. Okay. Pulmonary circuit, systemic circuit, very important. Arteries, capillaries, veins, right? So arteries travel away from the heart. They get smaller and smaller as they get away from the heart. So start at the, oops, wrong side. Start at the, start at the heart, beat, 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 go through my aorta, and aorta is big, slowly gets smaller until we get to what we call capillaries, which capillaries is where the exchange really starts to happen. The exchange of gases, exchange of nutrients from the bloodstream to the surrounding tissues. Blood is then collected into what we call veins, which drain from the capillary beds and return into the heart. Blood needs to, once blood is deoxygenated, denutrified, and brought back to the heart where it then can um, get oxygenated again. Uh, Nutrients primarily are coming from the digestive system. So that's also very important as well. These blood vessels have very specific structures, right? So we have a lumen, which is the space. That's where the blood is actually flowing. That's like the gap, the lumen. I can see you through my lumen. All right. The lumen is actually the space where the blood is flowing. But then around that, you have several layers of tissues called the tunics, right? So there's a tunic intima, which is the first set of layers, and then the media, and then the externa. The media is where you generally have the muscle, the smooth muscle that will contract. Remember, smooth muscle is controlled involuntarily. So you're not thinking about contracting your blood vessels, but they have to be able to contract to be able to control blood flow, blood pressure, things like that. We'll talk about that. So you have these three separate tissue layers, tunics, tunic intima, composed of endothelium, very similar to the inner lining of the heart, the endocardium, cardi. heart, endocardium. So this endothelium, it's a smooth surface. We want the blood to flow nice and smoothly when it's being pumped. Remember, it's being, you have these 60 to 80, sometimes 100, over 100 heartbeats per minute. You want that blood to flow nice and smooth. So you have this nice smooth surface of endothelial cells, which the blood can flow over with minimal friction, right? These are uh, uh, epithelial cells, squamous epithelial cells, which the blood can flow over. You also have elastic fibers give vessels a little bit of distensibility. So they have a little bit of stretch, a little bit of elasticity, so they can stretch and they can recoil. It's all in the tunica intima. Tunica media is that smooth muscle that I spoke about. That's where the smooth muscle is found. Also, some more elastic fibers called the external elastic lamina. Smooth muscle, you know, if the muscle contracts, the blood vessel constricts. Control the diameter of the blood vessel, therefore the amount of blood flow, right? So if I want more blood flow to an area, I can vasodilate. If I want less blood flow, I can constrict. That smooth muscle in the tunica media can constrict, right? It is innervated by our sympathetic. Remember the ANS, the autonomic nervous system, they have a sympathetic and parasympathetic. So the sympathetic can control this tunica media by the vasomotor nerves, and we get this vasoconstriction. So when the sympathetic is fired, your fight or flight is fired, fight, flight, um, part of your sympathetic, part of your autonomic nervous system that's fired, causes constriction. If we don't want constriction, then we want to inhibit the sympathetic nervous system, which causes vasodilation. Okay. The outer layer is the tunica externa, composed of dense, irregular, collagenous connective tissue, supporting the blood vessel, prevent it from overstretching. Right. And then we have this vasovasora, which are blood vessels that supply oxygen nutrients to the outsides of blood vessels, vessel to vessel, vasovasora, vessel to vessel, because the outsides of the blood vessels are too far away from the nutrients which are in the lumina of the blood vessels, and sometimes they don't get the necessary nutrients and oxygen, so they need their own blood vessels to supply blood to the outside of the vessels. And that is the structure of the blood vessel. So you have the inner layer, endothelium, smooth, simple, squamous, easy to travel over. You have the tunica media, that's where you have the muscle, and then you have the tunica externa, connective tissue, protects, keeps it from expanding too much, and protects the blood vessel. There are differences between arteries and veins. Okay, most arteries have a thicker tunica media, that middle layer, that smooth muscle layer. And they are more, their physiology allows for more control of blood pressure and blood flow to organs, which is very important. So artery, thicker tunica media than veins. And the internal and external elastic laminae are much more extensive in arteries than in veins. So arteries are under higher pressure. They're closer to the heart, so they're under higher pressure. So their internal and external elastic laminae, you see here, elastic laminae, that's part of the tunica media, elastic laminae. And then the internal elastic lamina is a tunica intima. So they help resist against the pressure that the blood vessel is experiencing, the blood pressure, the pressure that is exerted by the blood pushing on the walls of the blood, of the arteries of the blood vessels. So because arteries are under higher pressure, their internal and external elastic laminae are much more extensive. And because arteries can control blood pressure and blood flow, their tunica media, their smooth muscle layer is thicker. right? So that is artery compared to vein, artery compared to vein, right? The thickness of each component of the arterial wall depends on artery size. You have different uh, types, sizes of arteries, and different functions. So you have elastic arteries. Think of the aorta. You have muscular arteries, which can really control blood flow, and then you have arterioles, which are really your smallest arteries, right? So elastic arteries, largest in diameter. Think of the aorta. Feel feel a lot of pressure because they have the highest pressure, the closest to the heart. You have muscular arteries, intermediate in diameter, well-developed tunica media, that's where that smooth muscle is. And they have arterioles, smallest arteries, contain all three layers, intima, media, externa, um, that are extremely thin. And these feed into your capillary beds, which your capillaries are where you have the exchange of nutrients and gases and waste. You have arteries that also play a role in blood pressure. Um, we're going to talk about baroreceptors in the aorta and in the carotid, right? Which, when blood pressure increases, they have receptors that can send messages to the brain that can have a negative feedback response, cause your body to reduce your blood pressure. Could be there's many ways to increase and decrease blood pressure. For instance, if we increase the heart rate, that increases your blood pressure. If we decrease the heart rate, that decreases your blood pressure. Right? So we have this pressure receptors, baroreceptors in the aorta and the carotid. We also have chemoreceptors, which can detect blood oxygen, carbon dioxide. If my blood oxygen levels are low, I need to increase my heart rate so that I breathe more. I mean, my heart beats more and pump more blood, therefore get more oxygen into my blood. Right? Veins typically outnumber arteries, and their lumens have larger diameter. So we have more veins than arteries, and they have larger lumens. So more veins and larger lumens. That means there's more space in the veins overall. So 70% of your total blood is located in your veins at any given moment. Right? So your blood is sort of stored in your veins. It's not stored in your heart. Your heart is pumping, but it's sort of stored in your veins and working its way back to your heart. Veins typically have thinner walls, fewer elastic fibers, larger lumens than arteries. Right? So that's this chart is just showing you that how more blood is stored in the veins. That's more deoxygenated blood stored in the veins. And then you can see where the rest of the blood is in the body. Veins, like arteries, are classified by their size. You have the venules, the smallest veins, which drain blood from the capillary beds. And then they get bigger. Most veins have a thin tunica media, but they don't have that strong, smooth muscle layer that's very thin. They only can change vasodilate or vasoconstrict slightly. And many veins have valves. Because they don't have that well-developed tunica media, when you want blood to flow back to the heart, you don't want it to go backwards. So you have valves that can shut off along the way, prevent the blood from going backwards. And so these are the structures of elastic arteries, the aorta, muscular arteries, control blood pressure, arterioles, your smallest arteries that lead right into the capillaries, your venules, your smallest veins, and then your regular veins and their functions. Atherosclerosis, you may have heard of this, is a leading cause of death. Basically, plaque buildup, which builds up resistance in the arteries. Blood undergoes changes in velocity and flow. So your blood is not going to, you have this buildup of this plaque in your arteries. Therefore, your blood can't flow where it's supposed to go. When blood doesn't go where it's supposed to go, that means oxygen doesn't go where it's supposed to go. That means nutrients don't go where it's supposed to go. Obviously, that can lead to all types of issues. When parts of your body do not get the proper oxygen and nutrients, they die, right? This plaque can be generated by high blood pressure, cholesterol, infections, cigarette smoking, all things that they tell you not to do, right? Don't eat food high in cholesterol. Don't smoke. These things put you at risk for atherosclerosis and other types of heart diseases and problems in just in life in general. The plaque gets located in the tunica intima, the layer that surrounds your lumen, but it can also change your tunica media and change the rest of the artery. It becomes hard and becomes problematic. You start to obstruct blood flow. You can have what is called a myocardial infarction, a heart attack, or a stroke when blood flow is stopped. It can be very, very problematic. 10% of the world population has it. Okay, so um, don't smoke, don't eat foods high in cholesterol, exercise, help prevent atherosclerosis. It is very preventable. Vascular anastomosis or anastomoses. Um, this is where vessels connect via pathways called collateral vessels. And this can be when organs of the heart and the brain form new arteries. And this could be to meet a tissue's need. So part of your body needs more blood. We can form new arteries. So that can happen based on what needs your body has. And so that is the amazing part of the body. Remember, if you remember way back in chapter 1, we talked about growth and how growth is a sign of life and not necessarily growth. It doesn't always mean like I'm getting taller and growing in height, but it can be growth, right? In this, as an example like this, arterial anastomoses, where you're forming new blood vessels so that a tissue um, can meet its metabolic need. A tissue needs more nutrients, more oxygen. We can form new blood vessels, and that can happen, right? Right. Let's talk about blood flow. So, blood flows. We know that. And the physiology of blood flow is known as hemodynamics. Hemodynamics, right? So the heart pumps, provides a force, pressure is highest near the heart. The fluid in the heart, known as blood, moves from highest pressure to low pressure. Pressure is highest at the heart, lowest in the capillaries and the veins. It's going to move from the heart to the veins, move from high pressure to low pressure. Blood flows down the pressure gradient, right? Just think of anything. If you take a balloon, fill it up with water, and you squeeze it, it's going to go from the high pressure under the squeeze out the spout or out the end of the balloon to low pressure, which is the surrounding space around the balloon. Okay. Same thing happens in the heart. High pressure in the heart, those cardiac muscles are contracting, pushing that blood into the aorta. It's going to move from high pressure, the heart, to low pressure at the tissues. Okay. Blood pressure is just the outward force that blood exerts on the walls of the blood vessels. I'm sure everybody has heard the term blood pressure. We measure it in millimeters of mercury, and it can vary drastically. Obviously, it's highest at the heart and it's lowest the further you are away from the heart, right? So in the systemic arteries, it's going to be highest, and in the systemic veins, it'll be lowest, right? Because they're further away from the heart, right? So if I, if you have a, trying to think of an example, but I guess if you had like a hose and you were squeezing one end, like had a balloon on one end of the hose, squeezing water into the hose, the pressure will be highest where you're squeezing it. And then if that hose was 100 feet long, it'll be lower at the other end. Or if you think of like a river, where the river, uh, the further up you go on the river, the further towards the source you go, the higher the pressure is, versus where it's emptying out into like the ocean, the pressure is much lower. Magnitude of blood pressure is one of the factors that determines blood flow. So generally, blood flow matches cardiac output, 5 to 6 liters per minute. That's how much your heart is pumping. So it matches cardiac output. It's directly proportional to the pressure gradient, right? So as the blood flow increases, when the pressure increases, all makes sense. The harder you pump, more the blood flows. Resistance is any impedance to blood flow. So there are things we talked about, atherosclerosis, but there are other things that resist blood flow, right? Obviously, if the blood vessels constrict, that'll resist blood flow. If there's anything in the blood vessel impeding the blood vessel, plaque in the blood vessel, that'll restrict blood flow. So there are anything that resists any resistance will impede blood flow. Velocity with which blood flows is largely determined by cross-sectional area. The bigger the artery, the bigger the vein, the bigger the lumen, the more blood flow. The smaller the lumen, the less. It will change the velocity of the blood flow, right? So smaller vessels, total cross-sectional area increases. This increase in area causes velocity of blood flow to decrease. Right, so 3 main factors that influence blood pressure are resistance, cardiac output, and blood volume. Right, so peripheral resistance, any factor that hinders blood flow through vasculature contributes to overall resistance of that circuit. So vessels near the heart have little overall resistance. As you get away from the heart, the resistance is greater in the body's periphery. The peripheral resistance increases, blood pressure also increases, right? So peripheral resistance, blood pressure increases. Blood vessel radius, inversely related, right? So if I'm pumping something through a small vessel, the pressure's, and I'm, pumping it hard through a small vessel, the pressure is going to be high. But if I have a big space, a big vessel, and I'm pumping blood through it, the same pump, the pressure will be lower. So it's inversely related to the radius. And then we have viscosity, right? Think of pumping, if you were pumping water versus pumping syrup, it would be much different, right? That makes sense. The more viscous a liquid is, the more it resists being put into motion. Blood has a relatively high viscosity because it has proteins in the blood. Think of the plasma in the blood. It also has red blood cells, but also, we have protein in the blood plasma. So it has a high viscosity due to the numbers of protein that is contained. So it has some resistance to flow. It's going to increase blood pressure. Blood vessel length. The longer the blood vessel, the greater the resistance. So the more pressure that is needed to propel that blood through that longer vessel. But the longer the vessel, the less the more pressure you need to push the blood through, but the less blood pressure there is. So that's why in the the resistance in the pulmonary circuit is much lower than in the systemic circuit. Cardiac output, stroke volume, how much blood you're pushing out with each beat. So that left ventricle times heart rate, how many times you're pumping it out. Stroke volume times heart rate gets our cardiac output, right? Cardiac output and peripheral resistance factor into the changes in pressure, right? So if we change the cardiac output, we change the pressure. If we change the peripheral resistance, we change the pressure. Cardiac output increases, blood pressure increases, and vice versa. Right, small increases in blood volume are offset by ability of vessels to stretch. Remember, they have that ability to stretch the elastic layers in the tunica intima and the tunica media. Veins are most compliant vessels able to stretch to accommodate added fluid and blood volume increases. The small rise in pressure. Right? So this is your blood pressure sort of diagram here. You have radius, viscosity, blood vessel length, any obstructions, stroke volume, your stroke volume, heart rate, water loss, water gain, all determine blood pressure. So a lot of factors that can determine blood pressure. And like we said, blood pressure is different in different parts of the body. So blood pressure remains fairly low in the pulmonary circuit, heart to lungs. However, blood pressure changes significantly as blood travels through the systemic circuit, from the heart through the body, through delivering the nutrients and oxygen to the tissues. So systemic arterial pressure profile, the pressure profile of the entire systemic circuit is highest in the aorta and elastic arteries, declines as it spreads through the muscular arteries. So we have what is called this mean arterial pressure, average pressure in the systemic arteries, systemic system. The heart has both contraction and relaxation periods. And I'm sure everybody has taken blood pressure. Everybody has had their blood pressure taken, or maybe you have also taken blood pressure. But we have this systolic pressure, the pressure generated by the contraction. And we have this diastolic pressure at rest. Remember, you have a beat, you have this contraction where you're pushing, you feel that pulse, and then you have this relaxation where the heart is filling with blood. So that's your diastolic pressure. The difference between the systolic and diastolic pressure is called pulse pressure, right? And we take that usually with a sphygmomanometer meter and a stethoscope, all right? All right, and we listen for the sound, and you pump up that stethoscope around the artery. You pump it up to about 180, slowly let it off, and when you hear that first sound, that's your systolic pressure. That's the high number. That's the pressure when the heart is contracting. So you hear like turbulent blood flow when you first hear blood flow. So that equals the pressure in the cuff. So that's usually around 120. And then keep listening until you don't hear any sound. And that's considered your bottom number, your diastolic blood pressure, your pressure at rest. And then what we know is your mean arterial pressure is your diastolic pressure plus a third of your pulse pressure. Okay. And that's given our mean arterial pressure, or the general pressure around the entire system, the systemic system. How do we maintain blood pressure? Well, mean arterial pressure must be constantly maintained around 95 millimeters of mercury. And any deviation from this triggers our nervous system, our endocrine system, our urinary system. Notice all these different systems can help control our blood pressure. So that obviously means that blood pressure is something that is very important to control. All right, there's short-term and long-term controls of blood pressure. Right, so we have short-term control, primarily the nervous system, and some hormones of the endocrine system. Right, so we have sympathetic, back to that sympathetic and parasympathetic, the nervous system, the autonomic nervous system, uh, in its two divisions. So the sympathetic can release norepinephrine and epinephrine onto the cardiac muscle cells and the smooth muscle cells of the blood vessels, that tunica media. This can increase the heart rate, which increases your cardiac output, which will increase your blood pressure. Also can vasoconstrict the vessels, which also increases peripheral resistance, which increases blood pressure. Right? Parasympathetic, via the vagus nerve, can release acetylcholine on the sinoatrial and atrial ventricular nodes. This can slow the heart rate, decreasing blood pressure. Right? Most axons of the parasympathetic nervous system do not innervate smooth muscle cells of the blood vessels, right? So it doesn't interact with the blood vessels like the sympathetic nervous system, but they can inhibit. But what happens is that you inhibit the sympathetic neurons, and that causes the vessels to dilate. So when you have these parasympathetic neurons firing, you're inhibiting the sympathetic neurons, and therefore you get dilation. Right? So that's in that diagram there. Blood pressure goes down. Right. We have that baroreceptor reflex arc we talked about earlier. Right. So blood pressure increases above your normal range, and we have this negative feedback loop. So something negative happens. Your blood pressure increases above the normal range. Receptors, they sense that. The arteries are stretched because blood pressure has increased, and these baroreceptors detect that. Right? If I increase the pressure, I push on it, it stretches. The baroreceptors will detect that. Send a signal to the control signal. Send a signal to the control center, which is innervated by your cranial nerve. Impulses travel via parasympathetic afferent neurons to the cardiovascular center and the medulla oblongata. A decrease in sympathetic activity causes vasodilation. So we decrease the sympathetic activity. Remember, sympathetic activity causes vasoconstriction. We decrease sympathetic activity, causes vasodilation. Vasodilation causes blood pressure to go down. Right? We also have chemoreceptors. They can regulate breathing and respond to oxygen levels in the blood. So I need my blood oxygen levels are low. I need more oxygen. I need to breathe more, breathe faster. Right? Central chemoreceptors respond to decreases in pH of interstitial fluid in the brain, triggers another feedback loop that indirectly increases activity of sympathetic neurons, results in vasoconstriction and rise in blood pressure. Okay, so we have some chemoreceptors that can detect oxygen levels, control our breathing, increase our blood oxygen, and increase our oxygen intake, which increases our oxygen levels in our blood. And the reverse can happen as well. Hormones can control cardiac output. We already mentioned epinephrine, norepinephrine, but also thyroid hormones. Epinephrine, norepinephrine released from the adrenal medulla cause vasoconstriction, increased blood pressure, angiotensin 2, also vasoconstrictor, increased blood pressure, atrial natriuretic peptide AMP can also increase blood pressure. We also have what we call long-term maintenance of blood pressure, which is affected by our urinary system, which simply, if you think about it, the more water you put in the bloodstream, the more blood volume you'll have, and therefore the more pressure you have. The less water you have in your blood, remember the blood plasma is primarily water. The less water you have in your blood, the less pressure you'll have. So your kidneys, your urinary system can control your blood pressure by just simply controlling the amount of water that is in your blood. Right? So if we need the blood pressure to go up, it won't let as much water come out in your urine. If you need the blood pressure to go down, more water can come out. And you'll notice that when you take certain blood pressure medications, it causes you to urinate. If you have high blood pressure and you take blood pressure medications, some of them will simply cause more water to be eliminated from the body, therefore reducing your blood pressure by reducing the water content in your blood. And therefore, you will urinate more often. Okay. And that's what that is all about. All right, so this is blood pressure maintenance. There's disorders with our blood pressure. Blood pressure rises too high, falls too low, hypertension, high blood pressure. Uh, that's generally what we hear about, especially in America, high blood pressure. Our blood pressure is too high, over 140, 180, can go too high. That systolic pressure is too high. Hypotension is low blood pressure. Obviously, if I um, had an accident and lost a lot of blood, my blood pressure would go down, which can be very dangerous. They both are dangerous, but high blood pressure or low blood pressure can be very dangerous. Uh, Obviously, if I don't have enough blood pressure, the blood's not able to pump through my body, and therefore my organs, tissues won't get enough oxygen and nutrients, and then they can cause death that way. All right, capillaries and tissue perfusion. Let's go through this. So, capillaries generally are found in clusters called capillary beds. Blood flow to the tissue through the capillary bed is known as tissue perfusion. Right, this is how we get the gases and nutrients to the tissues. Capillaries are extremely thin vessels, walls only 0.2 micrometers thick, consist of endothelium uh, and small amount of basal lamina. You also have these pericytes, which are cells found around some capillaries, contain contractile filaments, which can control the blood flow in the capillary. Think of some of these small capillaries, so small that blood cells have to go single file through the capillary. They're pretty small. Capillary walls are joined by tight junctions. Okay. This is showing you capillary and showing you blood vessels, blood cells in a capillary. See, they're very small. Capillary exchange, we have movement of materials So we have diffusion and osmosis through the gaps in the pores. So diffusion, movement from high concentration to low concentration. Osmosis, diffusion of water. We also have fusion through membranes of endothelial cells. Carbon dioxide, oxygen are going to diffuse. We have transcytosis, the movement across the cell. So a larger molecule has to go in one end of the capillary wall and go out the other side of the capillary wall, transcytosis. So that goes back into chapter 3. Think of something being taken into the cell, endocytosis, and out of the cell, exocytosis. Right, so this is just showing you how movement across the capillary wall can happen. Different types of capillaries: continuous, fenestrated, sinusoidal. And just think of it as very simply as not leaky, more leaky, and very leaky. Right, so we have continuous capillaries located in the skin, nervous and connective tissue, muscle tissue. They're the least leaky. Then you have fenestrated capillaries, kidneys, endocrine, small intestines, moderately leaky. Then you have sinusoidal capillaries, liver, lymphoid, bone marrow, spleen, very leaky. Allow things a lot to pass through. So the leakier it is, the more things can pass through. Majority of capillaries are continuous. Tight junctions hold the capillary walls together. Least leaky, the fenestrated, a little bit more leaky. And then the sinusoidal is the leakiest. Right? It's a good way to remember those. And it's all based on function, where obviously in the liver, where you are processing a lot of the blood that is traveling through the body, you need leaky capillaries, sinusoidal capillaries. Okay? Blood flow through the capillary bed. So the flow of blood that takes place within the body's capillary bed is collectively called microcirculation. Right? So we have true capillaries, which you'll see in the diagram, and we have a central vessel, which and they help control blood flow by this precapillary sphincter. Right, so this central vessel, and then we have this like capillary bed, so to speak, and this precapillary sphincter, which can control the blood flow into the capillaries. So at rest, only about 25% of the body's capillary beds are fully open. Right? So your body can control what parts of the body are getting blood, nutrients, oxygen, right? It can control that. As the demand increases in certain parts of the body, your body can send more blood there, right? It's optimized. We see it here. We see the capillary. See the capillary here. See this channel here. The sphincter. See these sphincters here controlling blood flow. The venule here, smallest veins, the venule here, right? So these sphincters can cinch the capillaries so that they don't get blood flow, or open up so that they do get blood flow, depending on what's necessary. True capillaries are drained at the distal end of the capillary bed by a portion of the central canal called the thoroughfare channel. They drain and the blood does not flow backwards, but we want it to go in one direction only, into the venule. That's how blood flows. So if those sphincters are closed, blood's going to just flow from the capillary to the venule. If those sphincters are open, the blood will flow through the capillary bed. Tissue perfusion is regulated by local factors known as autoregulation. Okay, so this is, like I was saying, depending on what that tissue needs, we can regulate the blood flow to that tissue. So matching that tissue's level of activity. We have myogenic mechanism, counters change in blood flow by altering arterial resistance. Velocity of blood flow is related to inversely to resistance. So resistance increases, velocity decreases, and vice versa. So this mechanism slows blood flow by increasing resistance. When arterial pressure rises, mechanism speeds up blood flow by decreasing resistance when arterial pressure lowers, right? So it can maintain, control blood flow. You have metabolic controls mediated by chemicals present in the interstitial fluid, right? Certain chemicals, such as, that are generated when we're generating ATP. So if a cell is making ATP, then it has low concentrations of oxygen. Therefore, it needs more blood flow. If a cell is not generating a lot of ATP, or it doesn't need, it has a high concentration of oxygen because it's not using it up to generate ATP, then it doesn't need as much blood flow, right? So that's a metabolic control, right? So if that cell is, think about it, if that cell is generating ATP, it's requiring energy, oxygen levels are low, needs more oxygen. Where does the oxygen come from? Blood. The cell is not producing as much ATP, not using a lot of energy. Therefore, the oxygen concentrations are high because it's not using up the oxygen to make ATP. Therefore, we don't need as much oxygen. We don't need as much blood flow. So less blood needs to go to those tissues. There are some special circuits that exist. The heart is special. I heart you. You're special, right? But the heart receives 5% of the total cardiac output. Remember, the heart is only about the size of a fist, like a pound. Yet it receives 5% of the total cardiac output via the coronary circulation, right? So we have, blood has to, not only does the heart pump blood to the rest of the body, but blood has to be pumped, has to come to the heart. So it has its own perfusion pattern, which is opposite of the rest of the systemic circuit. Because when the heart pumps, when it's in systole, and that pump is happening, it is perfusion decreases. But when it's in diastole, when it's at rest, perfusion increases, right? Which is opposite to the rest of the body. The rest of the body, when the heart's in systole, when we have that pump, perfusion increases because blood's being pumped. But during diastole, perfusion decreases, right? The brain has 15% of the total cardiac output, right? It needs blood, it needs oxygen at all times, right? It's only 2% of the body mass, but 15% of the total cardiac output. If your brain doesn't get blood, and this is why CPR, cardiopulmonary resuscitation, is so vital, right? What are we trying to do with CPR? When we push on somebody's chest, we're trying to pump blood, basically act as the person's heart, hopefully temporarily until their heart starts beating again, because we want to get blood to the brain as quickly as possible, right? Because it's so vital. Skeletal muscle also has blood flow that can change dramatically. So when we exercise, it can increase as much as 50 times blood flow, right? So obviously, when you're not working out, your muscles don't need as much blood. They don't require as much oxygen. They're not burning as much ATP. But you are working out, you are exercising, you're utilizing those muscles, oxygen Oxygen is needed, carbon dioxide is high, blood flow needs to increase. Right, your skin, your largest organ in the body. Blood supply is located in the dermis. Oxygen and nutrients must diffuse from the capillaries in the dermis to the epidermis. Remember, the epidermis is avascular, so we need to regulate the blood flow to the skin. And that can change based on a number of different reasons. One of the reasons is temperature. As you see here, the body gets cold, or you're in a cold climate, or cold, it's cold outside. Less blood flow goes towards the surface of the skin. Your body keeps that blood more towards your internal organs so that your blood stays nice and warm, keeps your body temperature up. If it's hot outside, nice summer day, more blood flow can go towards the surface of your skin. Heat radiates off your skin. You sweat and heat radiates off your skin and you cool down. So blood flow can change based on your body's temperature. This next section can get a little bit tricky, so pay attention. So movement of water across the capillary is driven by a process called filtration. And there's a couple of different forces at work. We're going to talk about hydrostatic pressure and osmotic pressure, which explain how the movement across the capillary, movement of water across the capillary happens. Hydrostatic pressure pushes water out of the capillary. Osmotic pressure pulls water into the capillary, right? Remember, water moves from low concentration of solute to high concentration of solute. The solute is higher the solute is higher concentration in the bloodstream. So so moving according to the osmotic pressure, it will move into the bloodstream, but hydrostatic pressure, based on um, the blood pressure being pumped from your heart, is going to push water out of your bloodstream. So those two are opposing each other, and the net difference is going to show us the direction of water flow in your body. Right? So hydrostatic pressure, the force that a fluid exerts on the wall of a container. You have a beaker. Hydrostatic pressure is the pressure on the walls of that beaker. Blood is a fluid. Blood pressure is equal to hydrostatic pressure. So when we measure blood pressure, we're measuring hydrostatic pressure. Fluid flows from higher hydrostatic pressure or higher blood pressure to lower blood pressure. Hydrostatic pressure in capillaries changes from its arteriolar end, which is 35 millimeters of mercury, to its venular end, which is 50 millimeters of mercury. All right, so the hydrostatic pressure, the blood pressure, changes over the course of the capillary. All right, so here we have in this diagram, you see blood enters from the capillary near the arteriolar end. It's 35 millimeters of mercury, and near the venular end, it's only 15 millimeters of mercury, right? So that hydrostatic pressure is going to change over the course of going through the capillary and the capillary bed. This hydrostatic pressure is going to push water out of the capillary. Osmotic pressure, and this is where it can get a little confusing, the osmotic pressure involves the movement of water from low solute concentration to high solute concentration. So the osmotic pressure, the osmotic pressure is the force we must apply to prevent water from moving by osmosis. So it's naturally going to want to move from low concentration of solute to high concentration of solute, and the force that it would take to resist that movement is osmotic pressure. Right? So a solution with higher osmolarity has a higher osmotic pressure, right? You see it here below. more solutes, the more things dissolved in the water, the higher the water is going to want to move to balance out the concentrations. And the pressure that will resist that will be the osmotic pressure. The osmotic pressure of capillary blood is about 25 millimeters of mercury. Notice that's lower than the hydrostatic pressure. And so it's lower than the hydrostatic pressure in the arteriolar end, but higher than the hydrostatic pressure in the 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 venular, the end closer to the veins, the venules. Right? So this pressure is caused by proteins that are too large to leave the capillaries. So osmotic pressure remains consistent throughout the capillary's length. The difference in osmotic pressure creates an osmotic pressure gradient known as colloid osmotic pressure. Osmotic pressure is going to draw water into the capillaries. Right? So this is what is happening here. So you see closer to the arteriolar end, the hydrostatic pressure, the pressure created by your blood pressure, by your heart, is higher than the osmotic pressure. So the osmotic pressure wants to pull water in. The hydrostatic pressure wants to push water out. At the arteriolar end, the hydrostatic pressure is higher. So the net difference, 35 minus 25, is 15. Is 10. So the water is going to be pushed out. But at the other end, near the venule, we have the hydrostatic pressure is only 15 and the osmotic pressure is still 25. And so the hydrostatic pressure is lower, so therefore water will be drawn in. And so that's what we have is what we call the capillary net filtration pressure. The colloid osmotic pressure and hydrostatic pressure gradient work in opposite directions. Hydrostatic pressure pushes water out. Colloid osmotic pulls it in. The difference, net filtration pressure, just subtract the two, and you get the net filtration pressure, and you can see if the water is moving in or moving out at the arteriolar end, moving in near the venule end. Okay. And that's showing you how that happens. So water moves out and is drawn back in. Edema or swelling is characterized by an excessive amount of water in the interstitial fluid, the fluid that exists in the tissues and around the cells. One of the common causes is hypertension. Now think about that. Hypertension, high blood pressure, increase in hydrostatic pressure. Higher hydrostatic pressure means more water being pushed out of the arteries and the capillaries, less water being drawn in because the hydrostatic pressure is higher than the osmotic pressure, the colloid osmotic pressure. Therefore, you get more water left in the interstitial spaces, interstitial fluid, and therefore you have edema, collection of this water, and you have swelling. You particularly see it in the hands and the feet. So high blood pressure can cause this type of swelling. Right now we go to the anatomy of the systemic arteries. And this, you have the aorta, begins at the left ventricle. And we have the different branches of the aorta. You eventually get to a very important artery, the carotid artery. This is a diagram of your arteries. You have the internal carotid artery, which supplies the brain. Some more arteries here. Diagram of that. Some more arteries in the head and neck. A cerebrovascular accident or stroke, damage to the brain caused by disruption to its blood flow. Fourth most common death in the United States, caused by a blockage or loss of blood. We don't want to lose blood to the brain. Remember, we said that the brain gets 15% of the blood flow of the body. The brain needs its blood, it needs its nutrients, it needs its oxygen. It is constantly working. Head and neck. We have arteries of the thorax, arteries of the abdominal organs, upper limb. Femoral artery is an important artery. It's a distal continuation of the external iliac artery, serving the lower limb. You can also get your blood pressure on the femoral artery. Pulse points, so places where you can get blood pressure, you can feel the pulse of the heart, you can feel the beating of the heart. Increases during the ventricular systole and decreases during the ventricular diastole when the heart's at rest. This pressure changes causes the arteries to expand and recoil, and you can feel these different pulse points. The femoral pulse point is right in the inside of the hips. Usually we check the pulse at right around the wrist. That's the radial and ulnar pulse. Or you can take it at the brachial pulse. You can take it there. Some people take it at the carotid, uh, which we know is very close to the aorta, very close to the heart. You can also feel your pulse in your head, the temporal pulse. Those are your systemic arteries. Then there's the systemic veins. You can go through all of those. Three main veins that drain the head and the neck. The internal jugular, that's a very important vein. The vertebral veins and internal and then external jugular veins. See those there. Veins of the thorax and abdomen. Now, you have this hepatic portal system. Helps protect our bodies from nastier toxins, right? So chemicals that get digested in our body, example, alcohol, chemical, poison. People drink it all the time, but gets digested in our body, um, gets into our bloodstream, uh, goes through processing in what we call the liver through our hepatic portal system. The liver can um, neutralize, has enzymes that can destroy those chemicals and therefore protect our body from poisonous bottles of Jack Daniels and beer, right? So it gets processed. It's kind of interesting to look through. So you see uh, most of the blood from the abdominal organs goes into the hepatic portal vein instead of the anterior vena cava. So coming from the um, intestines, coming from the spleen, coming from the pancreas, even coming from the stomach, goes through this. Instead of going into the anterior vena cava, it goes through this vein hepatic portal vein. So it drains into that and then drains into the liver where it gets processed. And therefore, any chemicals can be destroyed after processing. The blood is delivered to the inferior vena cava via the hepatic veins, right? So that's how things that we ingest can be destroyed by the liver. Chemicals that we ingest that are bad for us, especially, can be destroyed by the liver. Obviously, if we have too many chemicals and the liver is taxed with destroying too many, and people who are alcoholics often run into this problem, where the liver it can't handle all the poison that you're giving it, and therefore you start to develop cirrhosis of the liver. Veins of the upper limb. That's the diagram of those. Lower limb, diagram of those. Then we also have what is called vein grafting, when blood flow through an artery is blocked as a result of atherosclerosis or another disease. You can bypass, and done by bypass graft, we can remove a vein and graft it onto an artery in two places to give blood an alternate route. This is modern medicine at its finest, right? So we can bypass a blocked artery. Obviously, best thing to do is not to get your arteries blocked by taking care of yourself, but if need be, we can bypass it. And that's amazing. Take a vein and use it to bypass the blocked part. And this is a list of your systemic veins. And that's the end of the show.